Okay, good day everyone. So in this video, we have to discuss another method in root finding in numerical method solution, which is Muller's method. Okay, so recall that the second method, as shown in figure A, obtains a root estimate by projecting a straight line to x-axis. So meaning denoted by this blue line. So I say projecting, it crosses the x-axis through two function values shown in figure A. While Muller's method, as presented in figure B, takes a similar approach but projects a parabola through 3 points, as you can see in the blue line. The method consists of deriving the coefficients of the parabola that goes through the 3 points, which is this one. So these coefficients can be substituted into the quadratic formula to obtain the point where the parabola intercepts the x-axis, that is the root estimate. The approach is facilitated by writing the parabolic equation in a convenient form. So we write a parabolic equation shown in figure B. So the parabolic equation denoted by figure B is, let us say, we have f2 of x equal to a, that is x minus x2 squared plus b times x minus x2 plus c. So what we have here is we want this parabola to intersect the 3 points, as you can show in the figure. Let us say xo. So the corresponding of this point xo is, the pair of xo is denoted by f of xo, as well as you can see in this point we have here points x1 and f of x1, and also here we have x2, f of x2. Okay, so we want these points, or we want this parabola to intersect these 3 points. So the coefficients of this equation can be evaluated by substituting each of the 3 points to give, let us say, for example, if we substitute these 3 points to this parabolic equation, we have, let us say, for f of xo, so for f of xo, we have a xo minus x2 squared plus b xo minus x2 plus c, as you can see in this parabolic equation. Next would be function of x1 would be, for the function of x1 we have, so a, we have x1 minus x2 squared plus b x1 minus x2, then plus c. Then lastly, in this point of this parabola, we have a function of x2, this a x2 minus x2 squared plus b times x2 minus x2 plus c. So what happened here is this is cancelled out. Okay, this is cancelled out. So it means that therefore we have a function of x2 equal to c. Okay, so let us continue in the next slide, representing the steps to follow in using Muller's method. Okay, there are the steps to follow in solving the complex roots in or using Muller's method. So number one is to evaluate the functional values of the initial approximation, such as f of x0, f of x1, and f of x2. Then second is compute the next approximation x3 as follows. So 2.1, we have solved that one as set c equal to function of x2. And then we have 2.2, section 2.2, we have to solve for uh, the 2 by 2 linear system for a and b. Okay, represented by this equation. Then 2.3, we have to compute for x3 equal to x2 plus minus 2c over b plus minus b squared minus 4ac. Choosing the positive or negative so that denominator is the largest in magnitude. So it means the largest magnitude will be computed. You will choose either positive or negative. The number 3, we have a test if x3 minus x2 over x3 is less than that of the error, or if the number of iterations exceeds n. If so, stop. Otherwise, go to step 4. Then step 4, relabel x3 as x2, x2 as x1, and x1 as xo. So meaning in step 4, this is a repeated for the next iteration. Okay, and then the same go process return to step 1. Need to evaluate again the functional values of the new initial approximations for the next iteration. So we have example here. Find the roots of the function of x equal to x cubed minus 2x squared minus 5, starting with initial approximations as x0 equal to -1, x1 equals 0, and x2 equal to 1. So the first step we have to is to evaluate the functional values of the initial approximation. So meaning we have to evaluate f of x0, f of x1, and f of x2. Okay. So for f of x0, we have f of -1. Okay, so we have to evaluate this one using the function -1 cubed minus 2 times -1 squared minus 5. So we have here -8, because -1 that is cubed, -1 minus 2 that is times -1 squared, this is also 1 times -2 minus 1 that is -3 minus 5 that is -8. Okay, so the next initial value of approximation will be f of x1. Okay, so the f of x1 is f of 0. So if you substitute f of 0 to the function, this is 0 cubed minus 2 times 0 squared minus 5. So we get the value of -5. Okay, and then next would be f of x2. Okay, so our f of x2 is f of 1. So f of 1 will be 1 cubed minus 2 times 1 squared minus 5, that is equal to -6. Okay, so we have done with the first step is to find the functional values of the initial approximations. Meaning the initial approximation is, I'm referring to the 3 values of x0, x1, and x2. Okay, so next is we have to compute for the next approximation, or x3, as follows. So to compute for x3, we'll set Okay, we have here. So again, we have to set C. So meaning we have to set C as f of x2, C. Okay. And then we have to solve the 2 by 2 linear system for A and B. So following, we have this 2 by 2 linear system, which is denoted by xo minus x2 squared, then x1 minus x2 also squared. So we have also xo minus x2, and then x1 minus x2. Okay, then we have to solve for A and B. So this is equal to f of x0 minus c, f of x1 minus c. Okay, so recall that our value of f of x0 is f of negative 1 is minus 8. So we have to substitute here. Our values of x0 is, we have values of x0 is negative 1 minus x2, which is 1. Then we have to square this. Then the second row will be x1, which is x1, that is 0 minus 1. Okay, and then squared. Next would be x0 is negative 1 minus 1. Then we have here x1 minus x2. We have x1 0 minus x2, that is, we have negative 1 here. Then again, copy a, b equal to function of x0 is, we have negative 8, and then c, we have setted c as fx2, that is negative 8 minus of minus 6. Then we have f of x1, that is negative 5 minus of minus 6. Okay, so we have to simplify this one. We have negative 1 minus 1, that is negative 2 squared, this is 4. 0 minus 1, this is negative 1 squared, this is 1. We have also here negative 2, negative 1, and then a, b. So this is equal to negative 8 minus minus 6, this is minus 2. Then negative 5 minus minus 6, that is 1. So again, simplifying this one, we have values of 4a. We have to perform row column of the matrix for, say, row column. So 4a minus 2b here. So 4a minus 2b. So this is equal to minus 2. And then we have also perform also a minus b equal to 1. So again, we have two equations here, so we can solve for a and b. So the value of a and b is, a is equal to minus 2, and while b is equal to minus 3. So again, we have computed already the values of a and b, so we need to compute for x3. So solving for x3, we have x3 equal to, we have the formula x2 plus negative 2c b plus minus v squared minus 4ac. So the value of x3, we have x2 is 1 plus negative 2 times the value of c is minus 6. Then we have v, we have a negative 3, so we have to choose plus or minus. Say for example, if you have minus b squared, if you squared negative 3 squared, that is 9. So 9 minus 4 times what is a, negative 2 times c, negative 6. We have value of here is 8 times 6, we have 48. Okay, so the value of x3 we have, as denoted, is we have the value of a complex roots. We have 0.25 plus 1.5612 I. Okay, so for the next iteration, we have to re-level x3 as our new x2, and x2 would be our x2 would be x1, and then our x1 would be x0. Okay, so this is our solution presented earlier. So again, preparing, we have already in the next iteration, which is the iteration equal to 2. So we have here I equal to 2. So it means that our x2 would be x3. Okay, so this is our new functional values. Then our x1 would be equal to x2. Our x2 we get is x1. X2 is 1. Okay, we have here. And then our x1 will be, our x0 will be the value of x1. So to compute for the new functional values, we have here function of x0, we have function of 0, since our value of our x0 will be x1 is 0, and then the value of our x1 will be x2, which is equal to 1, and our value of x2 is equal to 0.25 plus 1.5612 I. So if compute the value of our new functional values, we have f of x0, we have negative 5 shown in the function if we substitute f of 0 in our function, negative 5. So if f of x1 is f of 1, that is negative 6. Okay, as you can see that the value of here in the old functional values we get is, this is now becomes, the f of x1 would become the f of x0, and then the f of x2 becomes the f of x1 in the new functional values. Okay, and then we substitute the new f of x2. We have to substitute this uh, into the original function, which is we have to substitute 0.25 plus 1.5612 I, this is a cube, minus 2 times 0.25 plus 1.5612 I squared minus 5. So evaluating, we have this value. Okay, so again we have to set since we are the steps is repeated, so we have to set our new c equal to the function of x2. Okay, so let us continue. So we have here set as c equal to f of x2. Okay, we have to continue, or the process would be using the formula of the 2 by 2 linear system, which is here is the value of x0. This is the value of x0 here. X0 minus this is x2. This is x sub 0. Okay. So we have here a value of x0. We have here x2. Again, this is xo minus x2, and then our xo is 0, so meaning the negative is distributed. So this is x0 minus x2. Again, this is x1. We have here x1, x2. Also, this is x1 minus x2. Okay, multiply by a and b and equal to, this is f of x0 here. This is f of x0 minus c. So take note that our f of x0 here is minus 5. Minus that of the c, which is equal to negative 2.065 minus 5.0741i. And then also we have here this, we have f of x1 minus c. Okay, as you can see, this is a repeated process. As we have shown earlier in the solution we have presented, so by evaluating this one, we have get this value and then squared. Also this one, okay, this one is the value, then this one, and then evaluating this one, we have this. So evaluated this one, we have also this, and then copy this one, and then we will solve a and b using Kramer's rule. So this is now the result of this is now the fraction of this decimal notation of the matrix. This is the row 1, row 2, column 1, column 2. Okay, so further evaluation we have, so to get for the values of our a, we have to get also the delta. So if we get for the delta, we have to evaluate the determinant of this matrix. So we have this. So we have for 2 by 2 matrix, it is cross multiplying by the product of this element row 1 column 1 to element row 2 column 2, which is this one, and then minus the element of row 2 column 1 multiplied by the element of row 1 column 2. So the result is we have this, the determinant of delta, because if we solve for the value of a using Kramer's rule, we have a is equal to determinant of a over the determinant of delta. As well as for b, we have a determinant of v over determinant of delta. Okay, so next would be we have already get the delta, the determinant of delta, which is represented by this. And again, we have to proceed by finding determinant of a. So our determinant of a is we need to replace this value, the column 1, by this function, this right hand side equation. So as you can see, the column 1 is replaced by these values. Okay, so we have here, so again repeated by evaluating the determinant. So we have the value of determinant of a, which is this one. In order to get the value of a, we have determinant of a over delta. So we have also this one value. Again, for determinant of v, so again we have to replace the right hand side equation by the value of column 2. So evaluating, we have this one, determinant of v, we have this one, and also we can get the value of v. Okay, solving for x3, we have this one. So evaluated, so meaning you are very careful of this because you are now evaluating complex. So for evaluating complex raised to a real root or real number, you have to transform that into polar form. Okay, so our new x3 is this one, this value. Okay, so continue. So our new value of x3 is equal to negative 0.588 plus 1.19 um, I. Okay, so for the succeeding iterations 4 to 6, using the repeated iteration process we have presented in the solutions earlier, we get the iteration 4, we get the value of x3. Okay, x3. Iteration 5, we have also this one. As you can see, this is already, we have get already the root, since this is repeated already by repeated iteration 5 and 6. So we have to test for convergence, we have to test the error. So we have x3 minus x2 over x3, so we have this value of 5.1393 times 10 to the minus 4, and then we all know that this is the error is almost negligible for this value we get. So we stop here and accept the latest value of x3 as an approximation to the root. So we have conclusion here. Thus an approximate pair of complex roots is, we have this R1, we have this one, and then we have another, the R2 is the complex conjugate root of R1. And then we get the real root by MATLAB or calculator. Okay, to verify the roots of the function, we have the function we have earlier, or the function of this example, and then we need to get by using the factoring method. So we have x minus r1, x minus r2, x minus r3. So the result is this one. So therefore, we already get the value of the roots of this function. Okay, so let us continue. So this is the graph of the function of this function of x equal to x cubed minus 2x squared minus 5. So using MATLAB, the roots of function are this one. So this is the real root. And then what we have found here using Muller's method is the complex conjugate roots of this function. So the function can be graphed using MATLAB, and the roots of this function can be determined using graphical approach, as you can see. So this is the y-axis, and this is also the x-axis. So meaning the root always lies on the x-axis, and this is only representing the real root. Okay, and as a summary, the Muller's method is capable of solving imaginary roots as compared to the other methods that do not solve the imaginary roots. So Muller's method is an accurate method in finding imaginary roots, particularly in the complex roots or the complex conjugate roots of a function. Okay, and that is the end of my discussion, and thank you very much.